This call is now being recorded.
Can you see my screen?
Yes.
Okay, thank you. So, in the last lecture, we saw the basics of inverter interface, distributed generators, control types of grid-side converter, principles of VSG control, functions of synchronous block, governor block, QV droop block with PI in the VSG control mechanism. We also saw various other inverter control methods with virtual inertia, which is analogous to VSG developed in the past. And we also see the comparison in between them. Now in this lecture, we will see the comparison of dynamic characteristics between droop control and virtual synchronous generator control. The motto behind this lecture is to understand the difference of the two control methods caused by the presence of swing equation and the disadvantage of VSG control over traditional voltage source based grid supporting control. In this lecture, we will also see the small signal models of both methods, that is droop control and VSG control, for the case of single inverter operation and that of parallel operation with a synchronous generator. And also we will also calculate theoretical step responses of frequency change in order to understand the inertia effect caused by the virtual inertia. So let's go. As we have already discussed the VSG control mechanism, in order to understand the comparison between droop control and VSG control, let us recap the droop control. Basically, droop control is a control method for real and reactive power sharing by emulating parallel operation characteristics of synchronous generators. That is, droop control method mimics the steady state characteristics of synchronous generators. Droop control is one of the fundamental control technique for parallel operation of distributed generations, and droop coefficients are set according to the rating of DG so that it regulates active and reactive power according to their capability. And the fundamentals of droop control comes from the decoupled power flow equation. As we know that for a high voltage network, transmission lines have a very low RYX ratio, and for such system, real power mismatch are very sensitive to change in the phase angle, and reactive power mismatch are very sensitive to changes in the voltage magnitude. And contrary, for a low voltage network, lines have a very high RYX ratio in which real power mismatch are very sensitive to changes in voltage magnitude, and reactive power mismatch are very sensitive to changes in the phase angle. So accordingly, on the basis of these statements, as I told, there are two variants of droop control. First one is conventional droop control. This is also called P omega and QV droop control, and the second one is called reverse droop control, and this is also called as PV and Q omega droop control. And the first one, conventional droop control, which is accordingly to the fundamentals of high voltage network in with the line impedance is inductive. And the second one, that is reverse droop control, and which is based on the low voltage network in which the line impedance is resistive. But however, in the general scenario, it is preferred to implement conventional droop in microgrid distributed units due to several limitations of reverse droop. We generally prefer the conventional droop control over reverse droop control. We not use the reverse droop control in the microgrid distribution because of several limitations like compatibility with HV, compatibility with rotating generation, active power dispatch. That is, reverse droop is not compatible with HP system, and also not compatible with the rotating generators, and it is not able to do the active power dispatch properly. And the only advantage of reverse droop is that it has capability of direct voltage control. So actually what we do, we apply the P omega and QV droop control in LV network by adding virtual output impedance to make the total line impedance inductive. And the last point is that If we see the hierarchical microcontroller structure, root control usually plays the role of primary control. Actually, the aim of primary control is to provide like voltage stability, frequency stability, plug and play capability of DG, and avoidance of circulating current among distributed generators. And the aim of secondary control is compensating the voltage and frequency deviation caused by the primary control. And further, the aim of tertiary control is optimal operation in both operating modes and power flow control in grid tied mode. So coming to the next slide. And most loop control methods proposed in literature are voltage source based loop control. This is because the current source based loop control cannot provide voltage source for islanded microgrid. And a typical voltage source based loop control using P omega and Q omega is shown in this figure number 1. Here we can see that voltage uh, voltage and current sensor sense the voltage and current at the inverter filter output side and gives it to the power measurement block. And power measurement block calculates P out and Q out from the V out and I out and gives it to the P droop and Q droop block respectively. And here P droop block is based on the P omega droop control law and Q droop block is based on the QV droop control law. The inputs of P droop block are the measured active power, that is P out, and the set value of active power P naught, and gives reference angular frequency omega m according to the control mechanism of P omega droop. And the inputs of Q drop block are Q is the measured reactive power output, that is Q out, and the set value of reactive power Q naught, and gives output as reference voltage V reference. And further, here you can see the voltage control, the block voltage control. This voltage control is used to control the amplitude of output voltage to the voltage reference V reference. For this voltage control, there are variety of choices for us. The variety of choices for us. We can apply any various control methods inside the voltage control. It can either be a single voltage loop control or a multi-loop control. Multi-loop control. And the multi-loop control, as we know, composed of an outer voltage loop and an inner current loop. We will not go deep into this, the functionality of voltage control. And the output of this voltage control comes as the modulating voltage, which is the fed to the PWM block. And the reference angle theta m for the PWM comes from the integrator, which is present at the output of P droop block. So this is the brief working of conventional voltage source based loop control scheme. Now we will see separately the function of various block like P droop and Q droop blocks. So this is the insight of P droop block. Here Kp is the P omega droop coefficient, and the first order lag unit with the time constant Td is used to filter the high frequency ripples in the calculated P out. If measured output active power is suppose if measured output active power is greater than the set value of output active power, this P droop block lowers the output angular frequency omega m. Contrary, if measured output active power, that is P out, is less than the set value of output active power, this P droop block increases the output angular frequency omega m. If you want to express this whole block in the mathematical expression, we can write it as omega m is equal to minus P out minus P naught Kp 1 plus TDS plus omega naught. As I said earlier, you can hear, as I said, there were earlier 2 points. You can also verify from this mathematical expression. Suppose if P out is greater than P naught, this whole numerator part comes out to be positive, and then omega naught minus this value, thus the omega m decreases. And suppose if P out is less than P naught, the upper parts comes out to negative, and thus something will be added into omega naught, and and hence omega m increases. So from here you can also verify the working of the p droop. And the last point is the first order. This lag unit with the time constant is used to filter the high frequency ripples in the calculated output power. How we see the working of Q droop block in the case of conventional loop control technique. Here KQ the qubit droop coefficient and the first order lag unit with a time constant TD is used to filter the high frequency ripples in the calculated reactive power. And the whole mathematical and the whole block diagram can be expressed as in mathematical equation as V reference is equal to minus Q out minus Q naught divided by QQ 1 plus TDS plus E naught. And and similarly, if if we see the if we see the working, that if Q out is greater than Q naught, then the this parts this parts comes as positive, and the something is subtracted from E naught, and the V reference value decreases. And contrarily, if Q out is greater than Q naught, then numerator parts comes out negative, and this will whole becomes positive, and something will be added to E naught that increases the V reference. Thus this is the principle of the QV droop control law. And here one thing also important to mention, that the input and output of the governor model and Q droop controller of the basic virtual synchronous generator control is just reverse of the input and output of the P droop and Q droop controller of the conventional droop control. As we saw in the previous lecture, the input in the VSG control for governor model is omega n and output is the P in. But here you can see that input is P out and output is omega m for PV droop block, and for the QV droop block in the VSG controller, input is V out and output is Q reference. But in the droop controller, here input is Q out and output is V reference. So the both control mechanism has input and output reverse are just reversed in the case of droop control and the VSG controller scheme. How we further in this chapter to now what has been done by the author in this chapter, they simplify the model in order to focus on the active power control. So that here the active power control parts of both VSC controller and droop controller inactivated. Like in this, so as to deactivate the reactive power control parts of both VSG control and droop control, the output voltage of inverter E is fixed to the nominal voltage E naught, as shown in figure number 4 and figure number 5. Here you can see that the nominal voltage E naught is fixed. Here we can see that nominal voltage is directly fed to the PWM block in both the diagram. Now to derive the active power control equation of virtual synchronous generator control, we have to recap the swing equation and governor model equation of virtual synchronous generator. And this is the swing equation function of virtual synchronous generator, that is given by expression number, the equation 3. P in is minus P out is equal to j omega m d omega t d omega m by dt plus d omega m by omega g. And the same the governor model equation of VSG can be expressed as P in is equal to P out minus P naught minus Kp divided 1 plus TDS into omega m minus omega naught. And if we put equation number 4 into 3, we get the expression of active power control equation. That is that if we put P in is equal to P naught in this part in whole into this here, third in equation number 3, then we will get the active power control equation of virtual synchronous generator control in a single equation. So this is the active power control equation of virtual synchronous generator control. And this is the block diagram of a simplified virtual synchronous generator control without reactive power control. As we, as I told you earlier, the reactive power control part is inactivated and a fixed nominal voltage E naught is given to the PWM block. Similarly, this is the block diagram of simplified virtual synchronous generator control without reactive power control. And here we are also giving constant nominal voltage E naught to the PWM block instead of giving through reactive power control. There is no reactive power control part here in both the control mechanism. To simplify our analysis further. Now, what we do, we can easily neglect the effect of first order delay, so that we can easily compare the droop control and VSG control. We have to neglect the first order delay part so that it is easier for doing the analysis part. If we neglect the first order delay effect, then the active power control equation given in 5 of virtual synchronous generator can be expressed as this equation. Here I have here just remove this part, 1 divided by 1 plus TDS, that is comes out to be this equation. So the first order delay effect has been removed from the active power control equation. So this comes out to be this equation number 6. Similarly, if we neglect the first order delay effect also in the voltage source based droop control, then the P omega droop control equation can be simplified as omega m is minus P out minus P naught K divided by Kp plus omega naught. In the denominator, earlier it comes out to be 1 plus TDS. But further, if we neglect the first order delay, if we neglect the first effect of first order delay, then it will be eliminated, and the equation comes out as equation 7. So from these two equations, we can analyze two important things. And the following conclusions can be made from these two equations. If we put J is equal to 0 and D is equal to 0 in equation number 6, in this equation, put J is equal to 0, that is angular moment of inertia, and D is equal to 0, damping factor is equal to 0 in this equation, then the equation 6 becomes your similar equation as equation 7. So what can we say from this? That we can say that this both equation, if we neglect the that is written in the equation, if we just put moment of inertia is equal to 0 and damping factor is equal to 0, then the active power control equation and the P omega droop control equation of droop control mechanism both becomes equivalent. There is no difference between them. And thus we can say that droop control can be considered as a particular case of VSG control, in which both inertia and damping factor are set to 0. So this is one of the important conclusion that we can make from these two expressions. Now in the next section, we will do comparisons of transient responses of frequency. And for comparing the transient responses of frequency, first we will do small signal models of VSG and droop control for both single inverter operation and parallel operation with a synchronous generator. And further, based on these small signal models, a step responses of frequency change during a load transition are calculated. And from the step responses of frequency change, we analyze the inertia. That is, if lower df by dt comes, then that indicates larger inertia, and that is preferable. And if larger df by dt comes, then that indicates a smaller inertia. And we know that larger df by dt may leads to unnecessary tripping and load shedding, which is unavoidable. First, we see the single inverter operations, and here we can see the system model in the case of single inverter operation that is given by figure number 6. So here you can see this is distributed generators, and the output voltage of DG inverter is considered as EDG at the angle of delta DG, and the power comes from the DG inverter is PEDG plus JQEDG. And this is the output filter in which in which the only inductor is considered. The capacitor of output filter is usually neglected because uh, because the suspectance of this capacitor can be negligible at the fundamental frequency. And consecutively, voltage at the output filter, we can assume it as V out dg at the angle of delta dash dg, and the output power is P out dg plus jq out dg. And Z line dg is the transmission line impedance connected between the dg and load, and at the load bus voltage is considered as V bus at the angle of 0 degree. Here all the subscript dg indicates parameters related to distributed generation. DG means distributed generators. Here you can see all the subscripts in the written DG. And here you can see that the total output reactance and resistance can be taken as xdg is equal to xftg plus x line dg, and resistance we can take it as rdg is equal to r line dg. And this bus voltage is the RMS value of bus voltage, and delta dg is the power angle of distributed generators, that is angle difference between the virtual internal EMF and bus voltage. Now the power flow equations of ACDG coming out of the virtual inertia internal EMF EDG at the angle of delta DG from figure 6 can be expressed as equation number 8. You can see this is the power flow equations of the previous figure. This is the general expression of power flow equation in which resistance and reactance of line has been considered, and which both resistance and reactance of line we have considered. But now if we take the case of high voltage network in which transmission line is mainly inductive, then this expression can be simplified by considering RDG much less than XDG, and can be written as equation number 9. This the equation 8 becomes the equation 9 if we considered if we take the if we consider the high voltage line in which the transmission line is mainly inductive in nature. Now if the power loss in the power devices of inverter and in the output LC filter is neglected, then we can consider PEDG is equal to P out DG. Here you can see this PEDG becomes equivalent to P out DG if the power loss in the power device of inverter and the output LC filter is neglected. And for making the small signal relations, take the derivative of P out DG with respect to delta DG, and we will come as like this: delta P out DG is equal to K DG at the delta angle delta DG. For small signal relations, you would just have to do take the derivative of this part. P DG becomes equivalent to P out DG, so we have to just take the derivative of this part with respect to angle with respect to delta. So this comes out to be like this: delta P out DG by divided and this KDG is called the transient synchronizing power coefficient of the distributed generator. And one most important point here also is that for an inverter interface DG, the power angle delta DG is usually small, and therefore cos delta dg is approximated as 1. And we know that power angle is the derivative of angular frequency. So that this expression that can be expressed in a small signal model also as is delta dg is equal to delta omega m dg minus delta omega g. This omega m is the angular frequency of inverter, and this omega is the angular frequency angular frequency of rotor, and omega g the angular frequency at the infinite bus, that is load bus. So now if we put this relation in 10, now this relation is put in 10, then it becomes the expression 12, can be such 12. Now if we write the small signal model for the active power control equation, then it can be written as expression number 13. And since the frequency deviation from the nominal frequency is relatively small, then we can write then we can approximate this part is equal to this part omega m dg is delta omega m dg is approximated as omega naught s delta omega m dg. And further we also neglect the second order perturbation terms, and the equation 13 can be simplified as equation 14. Just remove this part and this part omega here the omega m dg is present, omega m dg is present, write it as nominal angular frequency omega naught s delta omega m dg. So we can get the expression as like 14. This equation we can also say as the simpler small signal model of the active power control equation of VSG. And further, if we neglect the line loss, then we can write delta P out dg is equal to delta P load. And eliminating delta omega g from this part. And this relation, this is very important relations comes out, and this transfer function tells the frequency change over a small loading transition. So what we are doing this most of the expression part and calculation part is to derive this relation that is given in question number 15. So this tells the frequency change over a small loading transition for a VSG control based distributed generation in the case of single inverter operation. As we have seen earlier, how the P omega loop control equation is similar to the active power control equation of VSG. If we considered j omega j dg is equal to 0, d dg is equal to 0. So here we get the transfer function for a loop control based dg can be obtained by assuming j is equal to 0 and d is equal to 0. In the same transfer function, we have to put j is equal to 0 and d is equal to 0, means angular moment of inertia and damping factor is equal to 0, so that we get the transfer function for the loop controller mechanism. And in other way, if we take s is equal to 0 here s is equal to 0, then equation 15 also becomes equivalent to express equation 16, which is the transfer function of loop controller dg. So here you can one thing we have to recap that we know that for a steady state of transfer function, we take limit s tends to 0. So this the steady state for a steady state response of VSG control mechanism gives the same expression for the loop controller. So we can also say that the steady state gain of equation 15 is determined by the loop coefficient kpdg and independent of the swing equation parameters. Means a steady state response of both VSG and droop control are same. And it's also important to means a steady state of VSG and droop controller are the same only if the droop coefficient, this KPDG and KPDG are set equally. And the plot of this figure 7 comes from by calculating a step response of DG frequency change during a small transition in the case of a small signal operation through equation 15 and 16, and the parameters for the calculation is given in the book. From the figure 7, we draw the following conclusions. We have just means in this figure we have just made the equation 15 and 16 responses in this figure number 7, and the conclusions we can draw from this figure are like first we can say that the frequency of VSG control changes slowly, whereas for droop control suffers a steep change. Here you can see this red curve is for droop control, and this one is for the BCD curve, means blue and brown, also red, all are for the VSG control. Here you can see that the frequency of means there is a steep change for droop control. Why there is a slowly change in the frequency of virtual synchronous generator control, not suffer response change. This implies that DG with VSG control has inertia, means this BCD part has inertia, which is due to the swing equation, and the DG with droop control has nearly no inertia. And secondly, we can what we conclude that larger value of JDG results in slower frequency change, which indicates the inertia of the DG determined by the J angular moment of inertia. If we compare B, C, and D, means in B and D part, the angular moment of inertia is considered as same. JD is equal to J naught, and here J naught. And here in C part, we have just half the angular moment of inertia. So here you can see that for C part, there is a means there is something not a better inertia than B and D part, and in B and D part they have large inertia because there is not a steep change over there. So this indicates that more the angular moment of inertia, more will be the less will be the slower the frequency change. So here you can conclude this second point. And third point is that here damping factor has barely no influence in the dynamic reference. Here D naught in all the values are set as D naught. There is no effect in this part, active power control equation part. So this has not effect in dynamic reference. And in all four cases, we can see that a steady states of all cases are the same. This verifies our previous conclusion that the steady state only depend on droop coefficient, that is KPDG. So a steady state of either VSG or droop control both are same. Now in the next section, we will do the small signal analysis of model in which DG is in parallel with the synchronous generators. In the previous section, we have done the small signal analysis of a single inverter operation. And in this section, we will do the small signal analysis of a model of DG in parallel operation with a synchronous generator. Previously, there is no synchronous generator in parallel with the DG, but here we can see that there is a synchronous generator in parallel with the DG. This study also important for the network with high penetration level of inverter interface DC. And in this case, it is preferred to study the rotor frequency change of synchronous generator, rather than DG, because the rotor frequency of synchronous generator is considered as the dominant one. And this figure 8 shows the system model of the case parallel operation with a synchronous generator, whereas subscript SG means SG indicates parameters related to synchronous generator, and DG subscript relates to distributed generators. Now, from the law of conservation of energy, we can write a equation like 17, number 17, delta P out DG plus delta P out SG is equal to delta P load. Means the power fluctuation in this DG plus this synchronous generators comes out to be delta P load. Now let us assume A is equal to delta P out dg, delta omega g plus, and B is equal to delta P out SG by delta omega g. Then equation 7 becomes the just modifying this equation 7 by in the form of A and B term also. So we get equation number 18. And further equation 12, which is the small signal, a small signal relation between change in output active power and change in angular frequency in case of DG, also holds true for synchronous generator, and we can write it as S P out SG is approximated as KSG delta omega MSG minus delta omega G, and further eliminating delta P out SG from 18 and 19 number equations, so that it comes out to be equation as 20. This is the whole mathematical part. We have to do the we have to finally get the finally transfer function for the analysis. And now further eliminating delta omega dg from 14 and 15, we get the equation as A is equal to delta P out dg by divided delta omega g, this transfer function of A. Since SG has synchronous generator has the same model as virtual synchronous generator, equation 1221 is also holds true for the synchronous generator, and becomes like this. This is for distributed generation, so we can write it as for synchronous generator. Similarly, as we did earlier, putting G is equal to 0 and D is equal to 0 means angular moment of inertia and damping factor is equal to 0. Then A for loop control can be obtained as means this transfer function for loop control we can also find out by putting G is equal to 0 and D is equal to 0. So we get like this. And one very important thing is that for synchronous generator, loop one for KSG and damping factor DSG are not constant and are dependent on the power angle delta SG and SG impedance parameters. For damping factor calculation, I already have shown in the equation in the previous lecture, and the equation for calculating the KSG for a silent pole synchronous generator is given in equation number 24, where here you can see xg the q axis synchronous reactance of synchronous generator, and eq dash is the q axis transient internal EMF. And further delta SG and eq dash can be calculated through equation 25 and 26 respectively, with measurement of synchronous generator output current Ig, ISG, and the angle phi SG. This phi SG angle is the phase difference between the V bus and ISG. So we will get the delta SG and eq dash. In the case of synchronous generator, we have to calculate KSG part and damping factor part, because this part is not variable as in the case of distributed is part variable here, but in distributed generator we are taking as constant. So we have to calculate these things. Now we have all the parameters, and the bus voltage, B bus, and fixed synchronous generator parameters can be found from the data sheet of book. Now, since we have all the parameters and it is possible to calculate the step responses of synchronous generator rotor frequency during a small loading transition, and the results are shown in figure number, the next figure, figure 9. So from the figure 9, that is a step response of synchronous generator rotor frequency during a load transition in case of parallel operation with various parameters. And the figure 10, which is just zoom in of figure 9, we can make the following conclusions. Like the case of single inverter operation, the distributed generators with VSG control can contribute more inertia to the system than distributed generators with droop control. Here you can see from the zoom in figure, means there is a steep change for the droop control, but for CDB, for BCD part, you can say there is a not a steep change in the frequency of the synchronous generator, angular frequency of synchronous generator. So here we can see that here there is distributed generator with VSG control, that is they are contributing more inertia to a system than distributed generation with droop control mechanism. Also here the same relation comes out as if they have larger moment of inertia like in B and D part, and C part just half angular moment of inertia, so they have more inertia than this C part. We can see that B and D has more inertia than C part. There is not uh, there is less frequency change in B and D part than C part, C curve. So the same relations, this conclusion can be made here also, that larger value of angular moment of inertia increases the inertia of the system. And here and here one another important conclusion, that the system with larger damping factor has slightly smaller oscillations. Like B and C have the same damping factor, and in just 10% of damping factor in D part. So here you can say there is more oscillations in the D part, and B and C part has lesser oscillation. So here we can also conclude that damping factor, those system which has larger damping factor has lesser oscillations. And in the steady state, we can see all the curves have the same response. So parameters of swing equation have no influence on the steady state. So both VSG and droop control has same response in the steady state. So that is all that is all about today's lecture. Thank you. Is there any question?
Hello.
Is there any question?
There is no question from my side.
Thank you. Thank you all for hearing me.